Afternoon, everyone. Welcome to this edition of the, let's call him today, the NITheCS Colloquium. As you know, NITHEC is in the process of being transformed into NITheCS. So at the moment, we are a little bit in a Schrödinger cat state where there is NITHEC and NITheCS and both are more or less alive. Yeah. And today we are very fortunate to have as a speaker, Professor Daniel Harlow from MIT. Yeah, and he will speak about symmetry in field theory and gravity. On the panel at the top of your screen, you see also Professor Robert de Mello-Koch from WITS. And Robert is the person who kindly organized for Daniel to be with us today. And I will ask Robert just now to introduce the speaker. And Robert will also moderate the Q&A session after or maybe during the talk. And as usual, you are on the list of panelists. You see also Dr. Sinaisky, who is the canonical co-host for this event, because he's kind enough to accept every time the offer to be the co-host. Yeah. To all the participants, just the usual reminder, please make use of the Q&A facility at the bottom of your screen. Towards the right, left of the red end button, so don't press the end button, or maybe raise your hands, and if you don't have too many raised hands, we will allow people to ask the question directly to the speaker after the talk. So Robert, can I kindly ask you to please introduce the speaker of today?
Sure. Okay, so it's a great pleasure to introduce our speaker for today, Daniel Harlow. So let me tell you about Daniel. Daniel completed a PhD in physics from Stanford University in 2012. He's been a postdoctoral fellow both at Princeton and at Harvard, and he has now joined MIT in July 2017. To tell you something about Daniel's work, Daniel has played a leading role in the discovery of new fundamental insights about quantum information, quantum field theory, and gravity. In particular, I'd like to mention that Daniel was a leading figure in a remarkable discovery in the context of ADS-CFT that showed that holographic duality is closely related to quantum error correcting codes. This work was extremely creative and significant, and in recognition of this, he was jointly awarded the 2019 New Horizons in Physics Prize. Daniel, we are all very much looking forward to your talk today. Please go ahead.
Thank you for that kind introduction. I'll try to live up to it. And thank you all for attending today. In general, this is kind of an abstract topic and questions are good. So please don't feel like you have to wait to the end of the talk to ask questions. You can type them into the Q&A and I'll try to stop occasionally and respond if there are questions. And if I don't stop for a while, Robert, maybe you can tell me if there are questions that are waiting. Sure. Okay, so I'm going to talk about this rather general sounding topic, symmetry and field theory and gravity. I guess at least for theoretical physicists, this is, probably this describes most of what we think about these days, somehow in some way. So indeed, symmetry is really essential in how we think about physics. So just to give you some reminders, right? Like in the standard model of particle physics, the structures of the interactions of the fundamental particles is controlled by a symmetry group, SU3 times SU2 times U1, or if you think about it, there's a quotient by a discrete subgroup, which determines how the strong and electroweak forces work, which particles carry what charges and so on. It all has to be consistent with this symmetry. Similarly, in Einstein's theory of gravity, which is general relativity, is also based on symmetry. It's based on the idea of being invariant under arbitrary coordinate transformations, which is kind of the mathematical expression of the equivalence principle. In atomic physics, transition rates are controlled by symmetries. So for example, the decay of the 2s state of hydrogen is very slow, about 1/10 of a second, which for an atom, 1/10 of a second is an eternity, right? And the reason it's so slow is because it can't decay only by emitting one photon, because that would be forbidden by angular momentum conservation, which is again a symmetry. In condensed matter physics, we usually classify phases of many body systems by talking about which symmetries are present and also which of those are spontaneously broken, which are not. So for example, the modern understanding of superconductors is that you have a U1 gauge symmetry, which is Higgs to a Z2 subgroup. And so there's a lot of stuff that was understood in some haphazard way before in the historical way of thinking about it. But once you understand that this is really what's going on, then everything else is essentially a consequence of this. This talk, I can't just talk about symmetry in general for the whole talk. That would be too broad. So I'm going to focus on this question of symmetries in quantum gravity, and in particular, I'm going to talk about some old conjectures, which some go back even to the 1950s, that propose restrictions on what kind of symmetry is possible in quantum gravity. So there are three conjectures that people usually talk about. The first is that there are no global symmetries in quantum gravity. So we'll discuss a bit later the meaning of the word global here. So there are gauge symmetries and global symmetries. Those are the two kinds of symmetries in physics. This conjecture says that the global symmetries can't happen in quantum gravity. Okay. Second conjecture, so gauge symmetries are allowed, they're not ruled out. But if you have a gauge symmetry, then this conjecture says that there must be physical objects that transform in all irreducible representations of the gauge group. So for example, you can have a Maxwell field, which has a U1 gauge symmetry. But if you do, then you need to have matter which is charged under it. So pure Maxwell theory would not be consistent. Pure Maxwell theory coupled to gravity would not be consistent with this conjecture number 2. And similarly for the first conjecture, right, like say the phi to the 4 theory coupled to gravity would not be consistent with the first conjecture, because there's a phi goes to minus phi global symmetry in phi to the 4 theory. And then finally, there's a third conjecture, which we won't talk about much in this talk, but which says that the gauge group has to be compact as a group. So none of these conjectures is obvious, because you can easily write down a Lagrangian of matter fields talking to gravity, which violates all three of these conjectures. In perturbation theory, you can quantize such a Lagrangian, and there's no problem with that. So if these conjectures are true, then they have to be some consequence of the non-perturbative consistency of quantum gravity. So there are various heuristic arguments for these conjectures. They've been around for a long time. There's a so-called empirical argument, which is that in string theory, they all seem to be true in all situations that we know. But until recently, there wasn't really a systematic approach for demonstrating, for proving these conjectures. And so what I'm going to talk about today is that in the last few years with Hiroshi Oguri from Caltech and from the IPMU in Tokyo, we wrote 2 papers. There's a short one and a long one, where we used the power of this NITheCS correspondence, which is sort of our best theory of quantum gravity so far, to show that all 3 of these conjectures are true within the correspondence. And so if you want to learn more about this, I strongly recommend starting with the short paper. I didn't update the journal reference. The long paper is now published in Communications and Mathematical Physics, but I forgot to update it. But anyway, the data compression factor in terms of pages between the long paper and the short paper is a factor of 35. So probably if you just want to learn a little bit, you probably want to start with the short paper rather than the long paper that's 35 times longer. So today I'm going to tell you a little bit about what these conjectures mean and also how we confirm them in ADS-CFT. But before I do that, I'll first stop and see if already there are questions.
No questions yet, Daniel.
Okay, thank you. But it looks like now there may be one. Why don't global symmetries exist in quantum gravity? Well, I guess that's what I'm going to try to explain in this talk, right? I don't think it has something to do. So when you talk about the universe being homogeneous and isotropic, that's a symmetry of the state, not a symmetry of the theory. So we're talking about symmetries of the theory. You know, when we say that phi to the 4 theory has a phi goes to minus phi symmetry, that's a symmetry of the theory, not a symmetry of, I mean, any particular state may or may not have that symmetry. Okay. So now let's try to unpack a little bit more what these conjectures mean, how we might try to prove them. So the first key point is that these conjectures treat global and gauge symmetries rather differently, right? I mean, global symmetries are not allowed, gauge symmetries are allowed. So it's very important to be clear about how these are defined and what the differences are between them. Since the conjectures treat them differently, we better define them differently. So just to give you some examples of the kind of issues you have to think about to get the definitions right? Like say, you know, in any quantum field theory or any quantum system for that matter, we could take a projection operator that projects onto the 42nd eigenstate of the Hamiltonian. So that projection operator is a Hermitian operator and it commutes with the Hamiltonian. So by the undergraduate definition of symmetry in quantum mechanics, it's a symmetry, right? It's an operator that commutes with the Hamiltonian. That's, you know, Hermitian operator. You can exponentiate it to get a unitary operator. But on the other hand, this is a pretty silly symmetry, right? Probably doesn't really deserve to be called a symmetry. In particular, in quantum field theory, this symmetry probably doesn't have a conserved current associated with it. So this is somehow a kind of a fake symmetry or something, a symmetry that's not really a useful symmetry. For gauge symmetry, the situation is even worse because, well, when we learn about gauge symmetry, what we're often told is that it's merely a redundancy of description. Okay, it's just some artificial choice that you have to make in describing a gauge theory. But then on the other hand, we also say that gauge theory is, you know, gauge symmetry is essential in modern physics. And this tension, I think, has probably bothered most physicists at one point or another in their life. For theorists, it probably has caused you pain your whole career. You know, which is it, right? Is it a mere redundancy of description, or is it an essential part of physics? Somehow, if it's just a mere redundancy of description, probably we shouldn't be making deep conjectures about redundancies of description. So it's got to at least be a little bit physical. Also, the fact that it's so useful probably means it's a little bit physical, but we're going to have to extract the physical part of it. So I don't have time to talk about it in this talk, but, you know, just understanding these basic questions about what are gauge and global symmetries actually has implications that go beyond just this question of what kind of symmetries are possible in quantum gravity. It even helps us understand several old problems in the standard model, such as how you're really supposed to interpret the decay of the neutral pion into 2 photons, or how you're supposed to define confinement in the presence of dynamical quarks. So, you know, those are 40-year-old problems, but I would say some of the confusion related to them, which has persisted till today, is related to not being clear about what you mean by gauge and global symmetry. And so then when we're clear about it, then we can understand those things better. But this talk is not about those things, so I'm just mentioning it here. Okay, I'll stop again just in case there are any questions. Looks like no. Okay, so that was kind of preliminary. Now let's try to think about, get into what we really mean by global and gauge symmetries. So what is quantum field theory? Okay, so that's a hard question. There are many ways that one could try to answer it. One way, which I like, is that we can think about it as a system with independent degrees of freedom at each point in space. So we have some kind of lattice like this one, at each site on the lattice, we have some degrees of freedom, maybe also on the links of the lattice if there are gauge fields, but local degrees of freedom on the sites, maybe the links, maybe the plaquettes, you know, it depends exactly what's going on, but localized degrees of freedom that are independent at each point in space. So the basic observables that we talk about in quantum field theory are local operators, like say the scalar field phi of x at some point x, or the electric field E of x, which are built only out of the degrees of freedom in the neighborhood of x. Okay, so you know, I have maybe, like for a scalar field, you can imagine I have a harmonic oscillator living at each of these dots. Okay, and then a local operator is something that's made just out of the oscillator at this dot and maybe its neighbors, but definitely not the dots over here. So that's kind of the basic structure of quantum field theory. Now, a global symmetry in quantum field theory is a symmetry in the sense of, you know, a unitary set of unitaries acting on the Hilbert space, which commutes with the Hamiltonian, but I'm also going to require that it acts faithfully on the set of local operators at each point x. So what that means is that if you take an operator, you know, one of these local operators that lives at some point x, and you conjugate it by this u of g, the unitary that represents the symmetry, then what you get is just some linear combination of other operators at the same point x. Okay, and this is an extremely constraining equation because it basically is saying that for a symmetry in quantum field theory to be a good symmetry, it has to be compatible with this local structure of quantum field theory. It has to take a local operator here and transform it into another local operator here, you know, not into some huge non-local mess. You know, whereas if I took like this projection onto the 42nd eigenstate of the Hamiltonian and I tried to conjugate by that, that would just give me some big non-local mess. So this is very constraining. It's the essence of global symmetry in quantum field theory. Faithfully just means that this D matrix here is non-trivial for every element of the group. Otherwise, you just haven't identified the symmetry group correctly. So, so here are some examples. So as I mentioned before, well, I said it in the field theory language, but in the Ising model, right, you can have a Z2 symmetry that flips the spin everywhere. And this is a global symmetry of the Ising model, or in quantum field theory, that becomes the phi goes to minus phi symmetry of phi to the fourth theory. Another example, maybe more familiar to particle physicists, is that in the standard model, there's a global symmetry which is generated by B minus L, where B is baryon number and L is lepton number. So that is an exact global symmetry of the standard model, as far as we can tell. It's possible that it could be broken if if neutrinos have Majorana masses, but we don't know whether they do or not. Now we should also say some things that are not global symmetries. So things which are not global symmetries are constant U1 gauge transformations in quantum electrodynamics. So gauge transformations where, you know, if A mu goes to A mu plus D mu lambda, if you take lambda to be a constant. So that rotates any charged fields, as we'll discuss a little bit later, but it's not a global symmetry. And the reason is that there aren't any local operators that are charged under it, because the ones that would be are not gauge invariant, so they're not physical. Another thing which is not a symmetry is this silly thing where you use the energy, the projection onto the eigenstate, as I just said. And yet another thing which is not a global symmetry is the so-called center symmetry in QCD. So if you know what that is, you know what I mean. If you don't, then don't worry about it. Now, for our purposes, the essential feature of global symmetry, which follows from this locality of the action of the symmetry on local operators, is that if you want to know how much global charge there is in a region of space, you just have to wander all over the region and look. You have to do a census. There's no way for you to know other than just to visit each site in the region and add up all the charges. And so that's mathematically expressed by saying that the charge in the region is the integral of a Noether charge, you know, the zero component of a Noether current for the global symmetry in that region. We just integrate it over the region. So for example, in the Ising model, if we want to know, you know, what's the net magnetization of a region, then what we should do is just visit all the spins in the region and see whether they're up or down, and then add up all the spins. Okay. And so that, for example, the Ising example shows that this idea is true also for the discrete symmetry, although you don't quite get to say that the charge is the integral of something. Okay, it looks like there's a question. Let me see. Does global symmetry imply local symmetry? No. Well, I guess let me think what you mean by local. Well, I'm not sure what you mean by local symmetry, actually. I mean, if you mean gauge symmetry, then the answer is no. So if you mean something else, then maybe, I'm not sure. I could interpret what you said as asking if Noether's theorem is true, which is saying if you have a global symmetry of quantum field theory, is there a current? The answer to that is almost always yes, but sometimes no, actually. Noether's theorem is actually not quite always true. There's some discussion of that in our paper. If you meant gauge, then yes. So no, it's definitely not, yes. No, but we haven't talked about gauge symmetry yet. We're about to. But before we do, let me ask if there are any questions about global symmetry, because now we're done with global symmetry for now. I'll just wait for a moment to see. We have plenty of time here, so you can feel free to ask questions as you like. I think my total number of slides is like 24 or 25, so you can see we're on pace. Okay, let's go on to gauge symmetry then. We're now experts in global symmetry. So the first notion of gauge symmetry that most of us learn about is that a gauge symmetry is like a global symmetry, except that the group element G is allowed to depend on position. So for example, in electromagnetism, we might write a transformation like this, where say psi is the electron field, where we say that psi prime of x is equal to e to the I lambda of x times psi of x. And well, if the lambda had not been allowed to depend on x, then that might have looked like a global symmetry, but since it's allowed to depend on x, then we traditionally would call it a gauge symmetry. As we were just discussing, you can have an action which is invariant under this transformation when lambda is a constant, but is not invariant when lambda is not a constant. And so then usually this is a stronger requirement saying that the action should be invariant under this also when lambda depends on position. Unfortunately, although this is what we learn in the textbooks and what we teach our children in kindergarten, most of these transformations are indeed just redundancies of description. That's what people say. And so indeed, we shouldn't be making conjectures about redundancies of description, right? Like it would be silly to make a conjecture that you can't have a redundancy of description, right? I mean, you can always have a redundancy of description. I can just add invisible unicorns to the theory and you can't stop me, right? So somehow if we want to make a conjecture that's meaningful, it shouldn't be about invisible unicorns, right? It should be about something that we can actually measure. So Hiroshi and I introduced a new idea which we called long-range gauge symmetry, which is designed to extract the physical part of the gauge symmetry without, keeping track of the redundant part of the symmetry. So the full definition is a bit technical. I'm not going to go through it in detail, but I'll tell you the basic idea in the next few slides. The basic idea is that instead of thinking about a symmetry which acts on local operators, so the global symmetry was a symmetry that acted on local operators, you should think about a gauge symmetry, or really a long-range gauge symmetry, as a symmetry that acts on lines that extend to infinity. Okay, so let me now try to motivate why that's the right idea. So the key difference between global symmetries and long-range gauge symmetry is that for a long-range gauge symmetry, if you want to know how much charge there is in a region, you don't need to go look everywhere in the region. For the global symmetry, we just had to go look everywhere and look at all the spins. For the gauge symmetry, we only need to make a measurement at the boundary of the region. So if you remember electromagnetism, which hopefully you do, this is something I teach to my students here at MIT. We have Gauss's law, right? So in civilized units, Gauss's law says that the electric charge in a spatial region R is the integral of the electric flux through the boundary of the region. And so you see this equation is quite different from the equation we had for global symmetry here, right? Here we said that the charge was the integral of the current density over the region, right? But now for gauge symmetry, we're doing an integral which is over the boundary of the region, right? We're looking at the electric flux through the boundary of the region. And there's some, that's the statement for electrodynamics. There's some more general statement is true for any gauge symmetry, for any long-range gauge symmetry. And intuitively, you can think about it like this. So, if you don't know what a Wilson line is, I'll say it on the next slide. But if you do know, here's a picture. But the idea is that charged operators in a gauge theory are always really attached to infinity by Wilson lines. And so you just need to detect the lines to know if there's a charge in here. And since any charge in here is connected to infinity by a line, that line's going to have to puncture the surface. And so what this electric flux does here is it just kind of measures how many lines are going through the edge of the region. And that tells you how much charge there is inside. So let's write it out just so make that a little more concrete, right? So in electrodynamics, we have the electron field psi of x. It's not gauge invariant, so it's not a good local operator. But we can make it gauge invariant by addressing it with a Wilson line, which is an integral of the electric potential, well, the electromagnetic potential, A mu, along a line from x to infinity. Okay. So this is a gauge invariant operator, because the gauge transformation of psi is canceled by the gauge transformation of the endpoint of the Wilson line. Now, the operator that implements the long-range U1 gauge symmetry in electrodynamics is the exponentiated electric flux through spatial infinity. So we just take the integral of E dot E through the two sphere at infinity, right? And then we treat that as a charge. Don't worry about where the Q's are. That just has to do with how you define things. And then this theta is the group element that tells you where you are in the group U1. And then if you conjugate this dressed operator by this U, right, then it transforms like e to the I theta. Okay, so the endpoint of the Wilson line transforms the endpoint at infinity transforms under this conjugation by the electric flux. Okay. So that's the basic idea of a long-range gauge symmetry. There's one technical point I should make, just in case there are any experts who are going to be unhappy otherwise. So this symmetry is only non-trivial if the gauge field is not in a Higgs or confining phase. Because if it is, then this flux just can't get out to infinity. It takes too much energy to send the electric flux out to infinity. And so all the states will be neutral. You won't be able to have any operators of finite energy that are charged. And so the symmetry won't mean anything in infinite volume. So in order to be sure that the symmetry is physical, you have to be in the right phase of the gauge theory. And so Hiroshi and I introduced some order parameter to confirm that you're in the right phase. And this order parameter can be used for many other things. You can, for example, also use it for diagnosing confinement, which is one of the things that I mentioned before. And it's kind of more robust than the traditional ways of trying to diagnose confinement. Okay, so that's it for gauge symmetry. Now let me pause again. Are there any questions about gauge symmetry or anything else I said so far? Okay. We've got one more round of preliminaries to do here. So now we understand global and gauge symmetry. We're going to now talk about global and gauge symmetry in ADS-CFT. But first I have to tell you a little about ADS-CFT. I don't want to assume that the audience is only ADS-CFT experts. That's not my understanding of what the audience is. So let's talk a little bit about ADS-CFT. So basic idea of ADS-CFT is like this, says that, well, the words are that quantum gravity in asymptotically ADS space is equal to quantum field theory on the asymptotic boundary. So on the left here, so what is ADS? So ADS is the universe with a negative cosmological constant. Asymptotically, ADS is the universe with negative cosmological constant, but also some matter floating around. So the geometry will backreact a bit. It won't be pure ADS. So on the left here, we have a person living in asymptotically ADS space. And so the only thing you need to know about ADS space or asymptotically ADS space is it's like living in a tin can. So you probably know that in our universe, the cosmological constant is positive, as far as we can tell. And so that causes galaxies to accelerate away from us with time. Right? So negative cosmological constant is kind of the opposite. It's like somehow the tendency is for stuff to come back to the center. And so in particular, if you're in the center here going up and you shine a laser pointer away from you, then it goes away for a while, but then it kind of turns around and comes back. And so you can see your laser pointer pointing back at you after a time which has avoided the radius of curvature. So it's somehow like living in a box. And so I've drawn the box as a cylinder here. So in all of these pictures, time goes up. So time is going up, and then a spatial slice is like this disk. So one way you can think about this is that it's like soup. It's like a soup can. Okay, so living in asymptotically ADS space is like living in the soup here. It could be tomato soup. Say here's the person in the middle of the soup swimming around. And then what the ADS CFT correspondence tells us is that somehow, although it's not obvious, the quantum gravity theory of the person living in the soup is actually microscopically defined by some quantum field theory that only lives in the can, in the metal part of the can, the outer part that's holding the tomato soup. And so in the quantum field theory description over here, there's no gravity, right? G is 0. Time still goes up. We still have some angular direction, but we no longer have this radial direction. That's just disappeared. So somehow that radial direction is emergent. It's not part of the microscopic description, or at least it's not fundamental in the microscopic description. And so this fact that the number of boundary dimensions is one less than the bulk number of dimensions is what's expected from the so-called holographic principle. So this is an illustration of that principle. So I tell you a bit more about the correspondence. So on a spatial slice, here's what the geometry looks like. It's represented by Escher. It has negative curvature, right? So you have this kind of Poincare disk kind of thing. And then the idea is that if you have a state in the Hilbert space on this side, it's equal to a state in the Hilbert space on that side. There's a one-to-one mapping between them. If you have a field in the bulk, say, so it'll depend on this radial direction, this time direction, and also I'm calling omega this angular direction. If you extrapolate a bulk field to the boundary by taking r to infinity, pull it out to here, then you get some local operator in the boundary conformal field theory. The Hamiltonian, this turns out to imply that the Hamiltonians are the same. So in particular, if you have low energy excitations in the gravity side, just little ripples going around in the Escher fish, then those correspond to low energy states of this boundary conformal field theory on the sphere. Whereas if you have very excited states in the bulk, which correspond to big, say like a big black hole filling some finite fraction of the space, then those are high energy quasi-thermal states in the dual CFT. Okay. Any questions so far about ADS CFT? I have one more thing to explain, but maybe already that's a lot. So let me pause and see if there are any questions about this. Okay. Let me continue then. So I need one more sort of more advanced feature of the correspondence, which is something called entanglement wedge reconstruction. So what entanglement wedge reconstruction is a rule so that tells us if we have a subregion of the boundary CFT that we'll call capital R, it tells us what subregion of the bulk we can learn about. Okay, and here's what the answer looks like. So this disk here is the same as the Escher disk in the previous slide. Okay, it's a spatial slice of the bulk. I just didn't draw the fish this time. I don't know, either because I was lazy or because I thought it would make the picture busy, probably a combination of the two effects. So this R here, this interval here, this part of the boundary circle, that's a spatial subregion of the boundary. And then I've shaded in this red region in the bulk, okay? And then the idea is that if I have an operator phi of x that's in the red region, then I can learn about it using only the CFT fields in R. Whereas if I have an operator over here, phi of y, that's not in the red region, then I can't learn about it only using the fields here. And in fact, I learn about it using the fields over here in the complement. And the dividing line between the two regions is that, well, here I've been drawing 2 + 1 dimensions. So I take a geodesic connecting the endpoints of R. In higher dimensions, I would use an extremal area surface of codimension 2. Can I please repeat how the radial coordinate vanishes in ADS? Well, I wouldn't necessarily say that it vanishes. So let's go to the picture where I had the radial coordinate labeled. Okay, so this disk here, right, I can use polar coordinates. So I have R going out and I have theta going around. So R labels where I am, where I am in terms of the radius of this Poincare disk. The thing that's maybe non-trivial is that in the dual description over here as a boundary conformal field theory, there's no radial direction. The boundary conformal field theory just lives on this gray shaded region here. Okay, so it doesn't like the operators and the local operators in the boundary conformal field theory are not labeled by this R. They're only labeled by T and theta. Okay. And so the fact that you have the R apparently on one side and not on the other side is kind of the mysterious thing of ADS-CFT. It says that quantum gravity in, say here, 2 + 1 dimensions is equal to quantum field theory in 1 + 1 dimensions. That's what I've drawn here, right? So the 2 + 1 is the interior of this can. The 1 + 1 here is the surface of the can. All right, so hopefully that makes it a little more clear. Okay. Are there dimensional restrictions? Yeah, so no, I wouldn't say it's demonstrably valid for all D. The highest number of dimensions that we know in actual example is that the boundary conformal field theory is 5 + 1 dimensional. So, and so for 5 + 1 dimensions and below, we know many examples from string theory. In higher dimensions, we don't know any examples. Now, that doesn't necessarily mean that it's not true and that there aren't examples that we haven't found yet. What we know is that if there are examples in higher dimensions, they can't have supersymmetry because there's just not enough supersymmetry to go around in higher dimensions. But there might be non-supersymmetric examples. I guess maybe the expectation is no, but I wouldn't say the expectation is based on much solid reasoning. Okay, so I apologize. This is the last thing that you have to learn before we now start trying to apply these ideas. Just this idea that if you have a boundary subregion R, so this interval on the right side of the disk, then the claim is that you draw the geodesic connecting its endpoints like this, and then this shaded red region, you can learn about all that just using the observables in R and not using the observables in its complement. Okay. I'll wait just 5 seconds to see if there are any more questions about ADS-CFT. Otherwise, we're now going to try to combine the two parts of the talk. Okay. Okay, so now let's use what we've learned to rule out the possibility of global symmetries in ADS-CFT. And so we do this by showing that but it's a proof by contradiction. So we show that if there were a global symmetry in the gravity side of ADS-CFT, then it would not be compatible with the local structure of the boundary quantum field theory. Okay. And since in ADS-CFT, the boundary quantum field theory is the fundamental description of what's going on, if that's inconsistent, then the theory is inconsistent. Okay. So indeed, let's imagine that there were a global symmetry, symmetry group G in the bulk. So using the various definitions that we talked about, so there will be some unitary representation of this symmetry group on the Hilbert space. So it'll be in the bulk by definition, and then by this dictionary, since the Hilbert spaces are the same, there will also have to be a unitary representation on the quantum field theory Hilbert space. And moreover, as we discussed, since boundary local operators are limits of bulk local operators, and since this symmetry acts locally on bulk local operators, it'll have to act locally on boundary local operators too. And therefore, it's a global symmetry of the boundary CFT. Okay, so maybe that sounds obvious. I say there's a global symmetry in the bulk, it must be a global symmetry in the boundary. But since we now have definition of the word global symmetry, we have to check. So, okay, we check and it's true. Okay, so there's global symmetry in the boundary CFT. Now, the claim, though, is that this is inconsistent. So it can't be a global symmetry in the boundary CFT. So let's try to understand why. So the problem comes from this local expression we had for the symmetry charge in a region R, right? We said that for global symmetry, if you want to know how much charge there is in a region, you just have to add up all the charges in the region. Okay, I'm using the notation for the case where the symmetry is continuous, but the argument will work also for discrete symmetries. So we can, what we can do, so here again, we have this disk. This disk is the time slice of the bulk. So I'm going to play a game. I'm going to split the boundary up into a bunch of regions. Here I've drawn 8. So you see R1 is this interval, R2 is this interval, and so on. And so the total charge on the boundary is going to be a sum of the charge in R1, the charge in R2, the charge in R3, the charge in R4, and so on, right? That's just the additivity of the integral, right? If you integrate over a bunch of disjoint regions, then the integral of the union is the sum of the integrals. Okay, if I said it correctly. Now, by assumption, there should be an operator which is charged, a bulk local operator which is charged under the global symmetry. Okay, otherwise, well, that was part of the definition. We needed it to act faithfully on the local operators. And so we can put this operator that's charged in the center of the space. But now we've got our contradiction because, well, so I took this Q and I just wrote it as a sum of the charge in this region, the charge in this region, the charge in that region, okay? But you see, the charge in this region is an operator that's only supported in this region. And so by this entanglement wedge reconstruction property that I mentioned of ADS-CFT, the charge in this boundary region can only learn about the thing in this shaded gray region here. In the previous thing, it was shaded red, now it's shaded gray. I apologize, it's the same region. And so the charge in the boundary charge in this region can't know about whether this operator is there or not, because it's not in this shaded region. So it can't know whether it's charged or not. But actually that's true for the charge in this region and the charge in this region and the charge in this region and so on. So each of these charges has to commute with the operator. But then if they all commute with the operator, then their sum has to commute with the operator too. And then it can't be charged, right? I mean, then it's not charged, and that's a contradiction because we assume that it was charged. So that's the argument. It's quite simple, really, actually. Most of the work is setting up the definitions. I guess mathematicians are familiar with that phenomenon. Just to sort of reiterate, you know, the local structure of the boundary theory required that the global symmetry charge could be split up into regions. And in each region, we have just the charge in that region. But the charge in each region is just too localized to know whether this operator is charged here because it's sitting all the way out here. But then if none of the pieces know, then the sum doesn't know either. Okay, and that's a contradiction. Maybe just to avoid confusion, let me emphasize that had we had a gauge symmetry in the bulk, we would not have had this contradiction because for gauge symmetry, the charged operator is attached by a line to infinity. That's what we discussed, right? And so that line will always get into one of these regions, no matter how small we make the regions. And so the gauge charge will be able to detect. And that's good because indeed all known examples of ADS-CFT have long-range gauge symmetries in the bulk, so we better not rule that out. Also, in the real world, we have gauge symmetries. So. Okay, so that's it for the no global symmetries conjecture. Any questions about that? Show the picture again. Okay, looks like there's a question. Let me so okay, good. So about higher form global symmetry. Yeah, so I was going to mention that at the end. So there's a version of this argument that works also for higher form global symmetry. So those are also excluded. Yes. That's in our paper. Is the entanglement wedge construction always true? Yeah, so, well, good. So there's a proof of it. So that's related to this quantum error correction stuff that Robert mentioned earlier. I didn't want to talk about that because that would be a whole nother talk. But yeah, so there's something in ADS-CFT which is called the quantum extremal surface formula, also sometimes called the Ru-Takanagi formula, which there's essentially a proof of it, roughly speaking. Certainly, I mean, maybe proof is not by the standards of mathematicians, but by the standards of physicists almost. There's almost a proof. And then this entanglement wedge reconstruction is a consequence of that. You can show that using this error correction technology. But for this talk, it's just a black box that we use. Okay, other questions? Okay. So let's now go on. So the other conjecture we're going to talk about, this conjecture number 2, was the conjecture that if there's a gauge symmetry, so that's allowed, but then there should exist objects that transform in all irreducible representations of the gauge symmetry. Now, we did the proof for a general gauge group, but there's some annoying group theory, which I guess most of you don't want to hear about. If any of you really love group theory, you can ask me after the talk. So to avoid the group theory, I'm just going to give the argument assuming the gauge group is U1. Okay, U1 is the group that hopefully we're all happy with. So then the set of all possible charges is just the set of integers. Okay, and so the conjecture is saying that we need to have objects of all possible charges allowed by charge quantization. So in fact, it's enough to have an object of unit charge, because once you have one of those, then by using that one together with its antiparticle, which has minus unit charge, you can combine them to make, for example, at least black holes of whatever charge you want. Now, I need to use one other thing. I lied. There was one other thing from ADS-CFT, but this one is not too bad. So there's this thing called the thermofield double state. So this actually has nothing to do with ADS-CFT. So people who know statistical mechanics will already be happy with it. It's just a sort of canonical purification of the thermofield double state. Of the thermal state. So you just take two copies of the system that you call the left and the right, and then you prepare this entangled state where you can see if you trace out one of the copies, then this just becomes a mixed state, which is the thermal state, E to the minus beta H, on whichever side you didn't trace out. So this is some, natural pure state in two copies of the system. It's reduced state on either side is the thermal state. So for ADS-CFT, this is two copies of the CFT on a sphere. So it was explained in some paper by Maldacena in the early 2000s that the gravity picture of this state is that it's the maximally extended Schwarzschild geometry, which maybe you heard, the spatial slices are wormholes that look like this. So they're wormholes that connect the left CFT to the right CFT. So basically, as long as you're happy with the idea that the Schwarzschild geometry is really a wormhole, then that's even probably enough for you to understand this argument, the argument I'm about to make. Okay, so then indeed the idea is that what we should do is think about in the CFT, how do we realize a Wilson line operator of unit charge that stretches through the wormhole from one boundary to the other? So just integral of A along this line from here to there, and then we exponentiate. So this Wilson line transforms under conjugation by the right electric flux. So if we take the electric flux through the right boundary, right, we have this Wilson line is ending there. And so if we conjugate it by this flux, then it transforms with a phase e to the I theta. Okay, that's what we talked about before for electromagnetism. But actually, then that means that we're done, right? Because that shows that the electric flux at one boundary, which is just the charge of the theory with one copy of the system, has to be a non-trivial operator for all theta from 0 to 2 pi. And that's only possible if there are states that are charged, right? Because this is just e to the iq. So if, for example, if q were 0, this would just always be the identity, right? So for it to not be the identity, and in fact, for it to be non-trivial for any theta, there have to be states of all possible charges, including unit charge. So then that already shows that the conjecture is true. Just even as soon as you write down this Wilson line, you understand that the conjecture is true. So now that may seem like you got something for nothing. So let me emphasize that the power of this argument comes from the fact that the Hilbert space of the two CFT copies is a tensor product of the left CFT and the right CFT, right? And this thermofield double state here is living in a tensor product Hilbert space. And so in order, what happened in that tensor product is what's really doing the work, because in order to represent this Wilson line on this kind of Hilbert space, you need to be able to break the Wilson line into left and right pieces, which you can only do using charged operators. So this is kind of a geometric graphical representation of the argument. Somehow you have to be able to cut the Wilson line, and that requires, in order to fit into this tensor product Hilbert space, and that requires charges. And in fact, these are precisely the charges that are required by conjecture number 2. Now I should also mention, so this argument applies also to 't Hooft lines, which are the magnetic duals of Wilson lines. And so it also predicts the existence of magnetic monopoles of minimal Dirac charge. And so maybe, from a phenomenological point of view, that's more interesting because we maybe think we already know that there exist electric charges of unit electric charge, although we don't actually know that. There could be one, the true microscopic charge could be smaller, but at least certainly we know there's some electric charges, and the ones we have are consistent with charge quantization. But we've never seen any magnetic monopoles, and this argument tells us that quantum gravity requires magnetic monopoles to be there. Okay. Unfortunately, I can't use it to tell you how they should be produced or how heavy they should be. So I can't tell you what the experiment is to find them, but I can tell you that they exist, at least as possible states of the theory. Okay, so any questions about this conjecture number 2? And then after that, I'll go to the conclusion. But first, happy to hear more questions. All right. Okay, so let's do the discussion now. So I'm just going to make a few comments about what we did and didn't accomplish. So as was already asked, so similar arguments apply also to higher form symmetries and space-time symmetries. So in this talk, I discussed internal symmetries, where when you acted on an operator at a point, you got back another operator at the same point. You could also talk about space-time symmetries like parity or time reversal, rotations, and similar arguments apply to all of those, and also to these higher form symmetries that at least one audience member knows about. Now, in case there are any quantum information theorists here, I should mention that this argument we gave for no global symmetries is related to a famous theorem in quantum information theory, which is called the Easton-Knill theorem. It says that quantum error correcting codes can't have continuous symmetries that act locally on the physical degrees of freedom. So I chose to not discuss quantum error correction in the talk because the talk is long enough already. But if you know about quantum error correction, then you probably know about this theorem. And so then for you, I'll observe that our argument can be viewed as a generalization of this theorem that applies to all symmetry groups, not just continuous symmetry groups, at the expense of having stronger assumptions, which happen to hold in ADS-CFT. Now, it's interesting to consider the limit where you take the gauge coupling of a continuous gauge symmetry to 0. So like you could say in electromagnetism, what if I take the fine structure constant to 0? What happens? Well, actually what happens is you get a global symmetry, and that's not allowed. So since this argument, I think, is fairly robust, then that also means that sufficiently small gauge coupling should also be ruled out. And so an argument like the one that I gave maybe can be used to give a lower bound on the strength of the gauge coupling, which is interesting. Again, in quantum field theory, there's no such restriction, right? A gauge coupling can be small as you want. But this argument would say that there's some lower bound. It can't be too small. And that's potentially interesting for phenomenology. For example, this B minus L symmetry that I mentioned could be a gauge symmetry with a very weakly coupled photon, but this would put bounds on that kind of scenario. Oh, somebody asked about the group theory. Okay, that question I'll answer at the end. So conjectures, just if there are condensed matter people here, they're probably already thinking this, but let me just say it. So this conjecture 2, number 3, and number 2 and 3, saying that you have to have all the charges and the gauge group has to be compact. These conjectures are quite natural from the point of view of condensed matter physics, where they hold automatically for any gauge field which is emergent. And in fact, that's actually kind of how I got into it, although I wasn't thinking about condensed matter physics. I was trying to use the emergence of the gauge field as a model for the emergence of space-time back in 2015. And I somehow realized that in this model, you had these conjectures automatically holding for free, and then that somehow was what led to the work that I've been describing here. But there are various interesting connections to the way condensed matter physicists think about emergent gauge fields. To make a closer connection to phenomenology, for example, like to think about, the stability of the proton or neutrinoless double beta decay, which are things that probe symmetry violation in the standard model, we'd like to get a better sense of how badly global symmetries have to be broken, and also how light the charged states that are required must be. So this is something that we're thinking about. So our arguments so far have dealt with the exact statement. But saying that global symmetries are impossible is not so useful if you're allowed to have approximate global symmetries that are sort of arbitrarily good. I mean, then, for all practical purposes, you have a global symmetry. So there need to be some epsilons and deltas put into these arguments. Finally, we'd also like to understand how do we go beyond asymptotically ADS quantum gravity? Because we don't live in ADS, right? We don't know for sure where we live, but we're pretty sure we don't live in ADS. So actually, last year, Edgar Shigulian and Edgar is a postdoc at UPenn, showed that the role of ADS CFT in the argument that I gave against global symmetries just now can actually be replaced by a more general conjecture about quantum gravity, which is called this quantum extremal surface formula that I mentioned before, which holds an ADS CFT, okay, but also is expected to be true more generally. And in fact, this formula is a generalization of the Bekenstein-Hawking formula for black hole entropy, and it's played a crucial role in recent insights into the black hole information problem. So Edgar and I our paper, the idea was to emphasize or explain that there's this new connection between the black hole information problem and the violation of global symmetry. And so this connection between the information problem and symmetry is currently being thought about by a bunch of people in many directions. So hopefully there'll be more to report soon. Okay, so that's it for me. Thank you for listening. I think I'm on time, and I'm happy to take questions.
Yeah, thank you very much, Daniel, for an excellent talk. And I'm sure Robert will guide us now through the question and answer session. I see there is still one question, I think, in the Q&A. But if people would like to raise their hand and ask directly a question, they're most and welcome to do so.
So maybe I'll quickly respond to the question in the Q&A. Yeah, so if you go to groups other than U1, so basically you have to use a theorem that says that every compact Lie group has the property that if you have a faithful finite dimensional representation, a single faithful finite dimensional representation, then by taking the tensor product of that with itself and its conjugate arbitrary number of times, you can realize all of the irreducible representations in the direct sum. So then you have to prove that theorem, which involves the characters and so on.
Thank you.
Okay, so no other questions right now, but Daniel, while we're waiting, I've got a question for you. So you were mentioning that this quantum extremal surface formula is expected to be true more generally than ADS-CFT.
Yeah.
Can you just explain what you meant by that?
Yeah, so, well, maybe the one way to think of, so currently there are two ways of understanding this quantum extremal surface formula. One way is based on the Euclidean gravity path integral. So just as the Euclidean gravity path integral can be used to derive the Bekenstein-Hawking formula in some sense, right, done by Gibbons and Hawking in the 70s. You know, it's the usual thing. You take the Euclidean Schwarzschild, you demand that it's smooth at the tip, and then you use that to compute a partition function. So if you accept that argument, which has various questionable features, but if you accept that argument, then a similar argument can be used to derive more generally this quantum extremal surface formula from the Euclidean gravity path integral, which doesn't rely on ADS-CFT. It's just the Euclidean gravity path integral. You can use it in other situations. Although, as always with Euclidean gravity, you don't always know what you're doing or how you're supposed to interpret things that you derive. I mean, Euclidean gravity can be a bit of a shady business. Okay. So that's one way of understanding why it should be true more generally. The other is that, so I and various other people developed this understanding of the formula as a feature of quantum error correcting codes. And in fact, I had a paper in 2016 showing that any quantum error correcting code obeys a version of the quantum extremal surface formula. And quantum error correcting codes are much more general than ADS-CFT, right? I mean, they're developed for understanding quantum computers. And so that shows that the basic phenomenon is very general. And it seems that it's you know, general enough to use, for example, in these recent calculations of the page curve for, you know, say black holes in ADS, black holes in flat space. I wouldn't say we know the full range of validity of the formula. We just have learned that it is true in many interesting situations. Let's see. Okay, I see two more questions in the chat. Shall I just answer them in order, Robert?
You're welcome. Yeah.
Yeah. So, have I thought about global symmetries and holographic complexity? Well, I've certainly thought about global symmetries, and I've thought about holographic complexity. I'm not sure that there's a relationship between them. I mean, for one thing, global symmetries are impossible. So, so once you show that something can't happen, then you're not so interested in connections with other things. I think that gauge symmetries, there have been some interesting issues with holographic complexity, where sometimes you, I get, for example, in particular for charged black holes, the various arguments people make about holographic complexity run into some interesting limitations. I think there have been some papers by Lenny and Ying Zhao and various collaborators about this for gauge symmetries. Let's see, the second question was this, the argument seems rather semi-classical. I think the quantum, okay, I think the quantum part was pretty important because we were using algebras of operators. So yeah, I mean, basically there were several ingredients that were pretty algebraic. So first we defined the symmetry in terms of how the operators acted on each other by operator multiplication. And then also, although it wasn't kind of explicit in what I said, there were various assumptions like you can get all of the states in the theory by acting on the vacuum with local operators in quantum field theory. So that was assumptions like that kind of went into some of what I was saying. On the other hand, it's true that, so I mean, somehow this, so although I didn't present it this way, the logic that I was describing kind of makes use of this error correction picture of holography. where you take things that are true in the sort of semi-classical regime, but then you see what the exact correspondence then tells you about how those have to fit into the full microscopic quantum description. And this tension that I had, like especially the part where I said that the symmetry charge could be split up into regions. So I could only make that argument if I assumed that the symmetry was really a full symmetry of the whole quantum gravity. If I only assumed that the symmetry was valid at low energies, I wouldn't have been able to split up the charge this way. And that then I wouldn't have had the contradiction. So certainly in that step, I had to really assume that the symmetry was a symmetry of the whole theory. I think it could be at least, it could be relaxed to an approximate symmetry of the whole theory. But what won't work is if you have an approximate symmetry that's only good at low energies. If you, I mean, because that can happen. I mean, we have that in the real world, right? So that better be allowed. So I needed something stronger than that. Hopefully that helps.
Good, Francesco. I think that's all of the questions answered.
Yeah, no, then probably the only last task is for me to thank Daniel very much for a really exciting talk that introduced probably many of us to very interesting recent results by Daniel and his collaborators. So Daniel, thank you so much. For the presentation. It was really nice. I really enjoyed it. And thank you as well to Robert for moderating the questions so nicely and for introducing Daniel, and most importantly, for inviting Daniel to be with us today. And the usual thank you to Ilya for being the co-host of the event. So to all the participants, thank you very much. Have a good evening, and please keep staying safe until we are all vaccinated. I know that Daniel is already, so that this is not for you.
Yes, thank you. I hope that you can all get back to a safe life soon.
Yes. We are slowly getting there. Yeah. So thank you very much, everyone. Have a good evening and a good day, Daniel, in your part of the world, and all the best. Yeah. Thank you very much. Bye.
Bye.